Welcome everyone, and thank you for joining me today. I'm excited to introduce our presentation on corrosion and its properties. In this session, we'll explore what corrosion is, its key characteristics, and why understanding it is so important. We'll cover the basics, look at some real-world examples, and discuss ways to prevent or manage corrosion. So let's get started and delve into this fascinating topic together. Corrosion can be broadly categorized into two main types, and understanding these categories is key to managing and preventing damage. The first type is wet corrosion, which is also known as aqueous corrosion. This occurs in environments where liquids or moisture are present, such as in humid atmospheres or directly in liquids. Atmospheric corrosion, a common example, happens when metals are exposed to air and moisture over time, leading to rust and deterioration. The second type is hot corrosion, which takes place at much higher temperatures, typically between 500 and 1200 degrees Celsius. This form of corrosion involves hot gases, and it's often encountered in high-temperature industrial processes, like in turbines or boilers. By recognizing these two categories, we can better understand the conditions under which different materials degrade and tailor our protective strategies accordingly. This distinction really ties into the overall theme of our presentation, which is about understanding corrosion mechanisms to improve material durability and lifespan. This slide highlights an important aspect of corrosion protection. Essentially, the passive film acts like a protective shield on the metal surface. It strongly adheres to the metal and serves as a barrier against the surrounding environment, preventing harmful elements from reaching the metal itself. This is crucial because it stops the electrochemical reactions that cause corrosion from taking place. And what's really fascinating is that if this passive film gets damaged locally, it has an incredible ability to heal itself. It can spontaneously repassivate, especially in an oxidizing environment, effectively repairing the protective layer. This passive film is incredibly thin, just about 1 to 3 nanometers, yet it plays such a vital role in maintaining the integrity of metal structures. So, in the context of corrosion prevention, the passive film is essentially the first line of defense, helping metals stay durable and resilient over time. Wet or aqueous, corrosion of metals is essentially an electrochemical process. It involves two critical parts, the anode and the cathode, as well as the electrolyte medium that connects them. At the anode, the metal undergoes oxidation, which means it loses electrons and forms rust or other corrosion products. You can think of it as the metal gradually breaking down as it gives up electrons. On the other side, at the cathode, reduction reactions take place. Depending on the environment, this could be oxygen being reduced or hydrogen being evolved. For example, in neutral or alkaline conditions, oxygen reacts with water and electrons to produce hydroxide ions. The reaction looks like O2 plus water and electrons producing OH. In acidic environments, oxygen reacts differently, combining with protons and electrons to form water. And in strongly reducing conditions, hydrogen ions gain electrons to produce hydrogen gas. All of these reactions highlight how complex and dynamic wet corrosion is. It's fundamentally driven by electrochemical processes, which means understanding these reactions helps us better predict and prevent corrosion in real-world scenarios. This ties into our overall theme of how to protect metals and extend their lifespan in various environments. Pitting corrosion is a highly localized form of corrosion, which means it occurs in small, discrete pits on the surface of stainless steel. These pits are usually visible as tiny holes or cavities on the metal's surface. When the passive layer that normally protects the steel gets damaged in a specific area, this spot becomes what we call an anode, where corrosion actively takes place. Meanwhile, the rest of the passive layer acts as a cathode, which actually helps to accelerate the corrosion process at that localized site. Because of this, the corrosion rate in that small area becomes quite high, and a pit begins to form. Inside the pit, the chemistry changes. Specifically, the hydrolysis of metal ions like Fe2+ and Cr3+ causes the pH to drop, making the environment more acidic. To balance out the positive charge of these metal ions, chloride ions from the surrounding environment migrate into the pit. This influx of chloride ions makes the corrosion process even more aggressive, allowing the pit to propagate further. This is a key concept because it highlights how pitting corrosion can be both highly localized and destructive. It reinforces the importance of understanding how damage to the passive layer and specific chemical conditions can lead to rapid material degradation. Recognizing these mechanisms helps us better prevent or mitigate such issues in stainless steel applications. This slide is about crevice corrosion, a specific type of corrosion that occurs in small, confined spaces or crevices. These crevices can form due to the design of components, like around flanges or threaded areas, or because of excess deposit buildup on surfaces. When these spaces form, they tend to have low oxygen levels, which makes the passive layer, that protective oxide film, quite weak. What happens then is similar to what we see in pitting corrosion. Dissolved metal ions from the metal surface lower the pH inside the crevice, making it more acidic. This acidity encourages chloride ions to enter the crevice, further destabilizing the passive layer. Over time, this passive layer can break down entirely, exposing the metal to a highly aggressive environment. Once the passive layer is compromised, corrosion accelerates rapidly within that confined space. This process highlights how important component design and surface conditions are in preventing crevice corrosion. It's a great example of how localized environmental factors can dramatically influence the overall durability of materials in our systems. So, it's well known that increasing the amount of chromium in an alloy, along with adding molybdenum and nitrogen, can significantly boost its resistance to pitting and crevice corrosion. These elements play a key role in making the steel more durable in aggressive environments. Now, to quantify this resistance, we use something called the pitting resistance equivalent, or PRE. Basically, PRE gives us an idea of how effective nitrogen is in the steel, along with chromium and molybdenum. The formula for PRE is quite straightforward. It's the percentage of chromium, plus 3.3 times the percentage of molybdenum, plus 16 times the percentage of nitrogen. This brings us to the ASTM G48 method, specifically methods E and F, which are used to test how resistant a material is to pitting and crevice corrosion. These tests involve exposing the material to a highly oxidizing environment, specifically a ferric chloride solution, 6% FeCl3 with 1% HCl, for 24 hours. Method E focuses on determining the critical pitting temperature, or CPT. This is the temperature above which pitting is likely to occur. Meanwhile, Method F measures the critical crevice temperature, or CCT, which indicates the temperature at which crevice corrosion can initiate. In essence, these tests help us understand how well a material can withstand aggressive conditions, which ties back into our overall goal of selecting materials that are both strong and corrosion-resistant in challenging environments. Now, let's take a closer look at how we evaluate the critical pitting temperature, or CPT, using a specific setup. We apply a 1 Na-Cl solution with an applied potential of plus 700 millivolts versus the saturated calomel electrode, or VSCE. This helps us simulate a corrosive environment similar to real-world conditions. An important aspect here is that crevice corrosion is avoided at the contact point between the specimen and the specimen holder. This ensures that the corrosion we observe is due to general pitting rather than localized crevice effects, providing more consistent and reliable results. We then increase the temperature in steps of 1 degree Celsius per minute. The critical point, or CPT, is defined as the temperature at which the current density exceeds 100 microamperes per square centimeter. So, essentially, when corrosion activity becomes significant enough to reach this current threshold, we've identified our CPT. This method aligns with the ASTM G150 standard, which provides guidelines for measuring pitting corrosion. Understanding this process is crucial because it helps us predict how materials will perform in aggressive environments and supports the development of more resistant alloys. Environmentally assisted cracking is a phenomenon that occurs when mechanical stress and a corrosive environment act together to cause material failure. It's not just about stress alone or corrosion alone, but the combination that accelerates cracking. One common form of this is stress corrosion cracking, which happens when a material is exposed to a specific environment that makes it more susceptible to cracking under stress. Then we have sulfide stress cracking, often encountered in oil and gas industries, where sulfide-rich environments cause cracks to develop in metals under stress. Hydrogen-induced stress cracking, or HISC, is another critical form, where hydrogen atoms infiltrate the metal, weakening its structure and leading to cracks. Corrosion fatigue is also part of this group. It's where cyclic loading combined with corrosion causes metal fatigue and crack initiation much faster than normal. All of these are examples of environmentally assisted cracking, and understanding them is crucial because they can significantly compromise the integrity and safety of structures and components. This overall theme highlights how environmental factors can dramatically influence material durability, especially in demanding industrial settings. Today, I want to talk about stress corrosion cracking, or SCC for short. This is a particularly insidious form of failure that occurs when a material is simultaneously exposed to tensile stress and a corrosive environment. What makes SCC so challenging is that it can happen even under very low stress levels that wouldn't normally cause cracking, especially over time. The key point to remember is that SCC involves a combination of mechanical stress and chemical attack. It's not just one or the other. This means that understanding the environment and the stress conditions is crucial for predicting and preventing it. SCC typically initiates at microscopic flaws or stress concentrators in the material, and once it starts, it can propagate rapidly, leading to sudden failure. That's why early detection is so important, especially in critical components like pipelines, reactor vessels, or marine structures. Connecting this to our overall theme of material integrity and safety, managing stress levels, controlling environmental conditions, and selecting appropriate materials are essential strategies to mitigate SCC risks. Remember, SCC isn't just about material failure. It can have serious safety and economic consequences if left unchecked. So, understanding its mechanisms helps us design more durable and reliable systems. Let's take a closer look at hydrogen-induced cracking. This is a particularly important failure mode to understand when working with materials exposed to hydrogen environments. Essentially, hydrogen can penetrate metals and cause cracks to form and propagate, often in ways that are not immediately obvious. The key point here is that hydrogen doesn't just sit passively. It actively weakens the metal's structure, making it more susceptible to cracking under stress. This type of cracking is especially problematic in high-strength steels and alloys, where even small amounts of hydrogen can lead to significant damage over time. It's crucial to recognize the conditions that promote hydrogen ingress, such as high pressure, temperature fluctuations, and the presence of corrosive environments. Understanding hydrogen-induced cracking is vital because it directly impacts the integrity and safety of many engineering systems, from pipelines to pressure vessels. By controlling these conditions and selecting appropriate materials, we can mitigate the risks associated with this form of failure. This ties back into our broader discussion on material durability and failure prevention, emphasizing the importance of proactive design and maintenance strategies. Sulfide stress corrosion cracking, or SSC, is a particularly insidious form of failure that can occur in environments containing hydrogen sulfide, which is common in the oil and gas industry. What makes SSC so dangerous is that it combines the presence of sulfides with tensile stress, leading to crack initiation and rapid propagation without any obvious warning signs. This type of cracking is especially problematic because it can happen at stresses well below the material's tensile strength, often under normal operating conditions. It's a classic example of how environmental factors and material stress work together to cause failure, highlighting the importance of understanding these interactions when designing and maintaining equipment. Connecting this back to our overall theme of corrosion management, it underscores the need for selecting proper materials, controlling residual and operational stresses, and implementing suitable protective measures. By doing so, we can significantly reduce the risk of SSC and ensure the integrity of our assets in sulfide-rich environments. Let's talk about corrosion fatigue. This is a specific type of failure that occurs when a material is subjected to cyclic stresses in a corrosive environment. Essentially, the presence of corrosion accelerates the fatigue process, making the material more likely to crack and fail at lower stress levels than it would in a non-corrosive setting. It's important to understand that corrosion fatigue combines two damaging mechanisms: the mechanical stress from cyclic loading and the chemical attack from the environment. When these two factors work together, the material's integrity deteriorates much faster. This concept is especially critical in industries like aerospace, marine, and chemical processing, where components are often exposed to harsh environments and cyclic loads. Recognizing the signs of corrosion fatigue can help us prevent catastrophic failures and improve maintenance strategies. So overall, corrosion fatigue highlights the importance of considering both environmental factors and mechanical stresses in our design and inspection processes, reinforcing the broader theme of ensuring material durability in challenging conditions. Stainless steel is exposed to aggressive atmospheres, which mainly leads to staining. It's important to remember that not all discoloration you see is due to corrosion. For corrosion to actually occur in the atmosphere, a conductive electrolyte must be present. This means that environmental factors like temperature, relative humidity, and other weather conditions play a significant role in how the corrosion process unfolds. Additionally, dirt, dust, and even corrosive chemicals in the environment can increase the material's susceptibility to atmospheric corrosion. These elements can break down the protective surface layers or create more aggressive conditions, speeding up deterioration. Understanding atmospheric corrosion is crucial because it highlights how external environmental factors impact the durability and appearance of stainless steel in real-world conditions. By controlling or minimizing these environmental influences, we can better protect stainless steel and extend its lifespan. This slide focuses on the phenomenon of intergranular corrosion, which mainly occurs at grain boundaries and is a consequence of chromium carbide and intermetallic phase precipitation. This type of corrosion has been a potential risk for stainless steel, particularly because of its high carbon content, typically ranging from 0.05 to 0.15%. However, with the use of method AOD, or argon-oxygen decarburization, during steelmaking, we can significantly lower the carbon content. This reduction in carbon has helped decrease the risk of intergranular corrosion. Now, the core issue arises when chromium carbides precipitate at the grain boundaries, usually between 550 and 850 degrees Celsius. This process depletes chromium in the areas surrounding the carbides, creating what we call a sensitized zone. These zones are more susceptible to corrosion attack along the grain boundaries, which can compromise the steel's integrity. To prevent this, it's important to minimize the time the steel spends in the sensitization temperature zone, or to perform solution annealing at higher temperatures between 1000 and 1200 degrees Celsius. Doing so helps dissolve the carbides and reduce the chances of intergranular corrosion developing. So overall, controlling the carbon content and heat treatment processes are key strategies in managing intergranular corrosion risks in stainless steel. This slide doesn't contain enough information. That's why we're moving to the next slide. Galvanic corrosion occurs when two different metals are electrically connected and are exposed to a corrosive environment. Essentially, if you have dissimilar metals in contact and there's moisture or other corrosive elements present, one metal can start to corrode faster than it normally would. The key point to remember here is that the greater the difference in the galvanic series between these two metals, the higher the risk of galvanic corrosion. So, metals that are far apart on the galvanic series are more likely to cause problems when connected. This is especially important in our overall discussion of material selection and maintenance, because choosing compatible metals can significantly reduce this type of corrosion. Understanding these principles helps us design more durable and corrosion-resistant systems. This occurs when metal is exposed to hot atmospheric oxygen, sulfur, halogens, and other aggressive elements. These environments can cause significant damage to materials, especially at high temperatures. The types of high-temperature corrosion include oxidation, sulfidation, carburization, and nitridation. Oxidation is probably the most common, where metals react with oxygen to form oxides, which can weaken the material over time. Sulfidation happens when sulfur compounds react with the metal, creating sulfides that can be quite destructive. Carburization and nitridation involve the diffusion of carbon and nitrogen into the metal's surface, leading to hard, brittle layers that compromise the metal's integrity. Understanding these different types of high-temperature corrosion is crucial, because it helps us design better materials and protective strategies, ultimately improving the longevity and safety of components operating in extreme environments. When stainless steel is exposed to an oxidizing environment at elevated temperatures, an oxide layer forms on its surface. This oxide layer acts as a protective barrier, but its effectiveness depends on its composition. Chromium plays a key role here by forming a layer of Cr2O3, which significantly increases the steel's resistance to oxidation. As the chromium content increases from 0 up to about 27%, the maximum service temperature that the stainless steel can withstand also rises, going from around 500 degrees Celsius up to approximately 1150 degrees Celsius. This shows how critical chromium levels are in enhancing high-temperature performance. However, the sensitivity of this protective oxide layer to temperature variations can be an issue. To mitigate that, manufacturers often add reactive metals like yttrium, hafnium, or rare earth metals such as cerium and lanthanum. These elements help stabilize the oxide layer, making it more resilient across different temperature ranges. It's also important to note that the presence of water vapor in the air can reduce the steel's resistance to oxidation. Water vapor accelerates the oxidation process, which can compromise the integrity of the protective layer. Lastly, if the chromium content falls below a critical level, the chromia scale cannot reform effectively after it's been damaged or disrupted. Without that protective Cr2O3 layer, the steel becomes much more susceptible to rapid oxidation and degradation at high temperatures. Sulfidation is quite similar to oxidation in terms of the chemical process involved. However, a key difference is that sulfides tend to have lower melting points compared to oxides. This means that, under high-temperature conditions, sulfides can actually be found in a molten phase on the surface of the material. This is particularly important when we look at nickel, because it can form low melting point nickel-sulfur compounds. These compounds can cause rapid deterioration of steel, which is a major concern in many industrial applications. Another critical point to remember is that sulfide scales are generally less protective than oxide scales. This makes the material more vulnerable to further corrosion and damage. So, when we think about sulfidation, it's essential to understand how these lower melting points and less protective scales contribute to the overall degradation of metals, especially in environments where sulfur compounds are prevalent. Let's talk about carburization of stainless steel. This process occurs in the presence of gases like carbon monoxide, carbon dioxide, methane, and other hydrocarbons, especially at high temperatures. When these gases interact with the steel, carbon atoms diffuse into the metal, leading to changes in its properties. Now, one critical consequence of this process is the precipitation of nitrides and carbides within the steel. This precipitation can cause embrittlement, making the material more brittle and reducing its ductility and toughness. Essentially, the steel becomes less able to absorb energy without fracturing, which is a significant concern in many applications. It's also important to highlight that there's a more severe form called catastrophic carburization, often referred to as metal dusting. This typically happens at lower temperatures, roughly between 450 and 700 degrees Celsius. Under these conditions, the steel can rapidly degrade, resulting in the formation of a dust-like metal powder, which can be highly dangerous and damaging to equipment. Connecting this to the overall theme, understanding carburization and nitridation is vital because they directly impact the durability and safety of stainless steel components in various industrial environments. Recognizing the conditions that lead to these processes helps us better prevent failures and extend the lifespan of the materials we rely on. Thank you so much for your time and attention today. I really appreciate your engagement throughout this presentation.